Great, fantastic. So I'm here to talk to you a little bit about what's changed in this field in the last 5 or so years and sort of convey why this is still an active area of research. So just to summarize what my colleagues have told you so far, so Shivaji started out by telling us how topology has really changed how we view phases of matter, both in how we classify phases and how we understand their excitations. Steve, I put the disclaimer he should have put on there that says that these topological ideas could even be useful in certain contexts, particularly in terms of anyons. But in spite of Microsoft's $1 billion investment, Oxford Physics does not endorse you putting any money into any quantum computing that way. So just to cover our bases. So a lot of what Steve said, somebody said, these ideas are recent. They are recent. They're recent on the time scale of physics you see in textbooks, but they're not that recent in the time scale of the physics that people write papers on. So if you think about it, a lot of these ideas were already there and in the ether in the 1990s and 2000s. So a question is, why might this be still something that's a field of active research that Steve and I, for instance, spend our days thinking about, or at least some fractions of our days thinking about it when we're not doing admin? And why in 2025 is this more interesting, and much more interesting than 2015? So what I'm going to try and tell you is a little bit about the sort of very recent history and what happened between 2015 and 2025 that made this interesting. And to tell that story, I want to tell it to you in sort of 3 chapters or 3 ideas, and how those 3 ideas kind of connect these what Shivaji and Steve talked about. And the 3 words I'll use are topology, correlations, and tunability. And in some sense, tunability is the thing that's really changed, and I'll try and explain why that changed in recent years. And so what I want to get across is, how does the sort of original, the vanilla version of the quantum Hall effect embody these ingredients? Because that'll give us an idea of why taking those ideas and making them work in other systems was hard, and what changed. And I want to try and explain why that's challenging and how people actually manage to do this. So that's the story that I'll try and take you through today. Okay? So going back to basics, this is sort of a classic exercise in that we give our second-year quantum mechanics students. We ask them, what happens to the quantum mechanics of an electron moving in a magnetic field if it was forced to be in 2 dimensions? So famously, there's a Lorentz force. So classically, instead of moving in straight lines, electrons will form circular orbits. But quantum mechanics tells us that periodic orbits must be quantized. And there's an elementary way of quantizing it, which basically thinks about Aharonov-Bohm phases that the electrons experienced. So, there's a calculation. You would, work through it. Your tutor would, check your h-bars and complain about various factors. But in the end, if you did it all right, what you should find is that instead of our happy p squared over 2m free particle dispersion, you get a series of energy levels that look bizarre, because these look like the energy levels of a harmonic oscillator, but in 1 dimension. And what happened is that 1 dimension's worth of kind of motion of the electrons went into these levels being very, very degenerate. And roughly, a way to think about what happens in this kind of problems is that if we think about the particle moving around, we can actually calculate the phase it accumulates. And Aharonov and Bohm tell us that that phase is some set of fundamental constants here in CGS land, multiplied by the flux through that unit. And if you work this out, this turns out to be dimensionless. And when this angle, when this phase is 2 pi, it turns out one can think of that as defining a new unit cell for the particle. So, in free space, there's no unit cell. All coordinates are created equal. But once you put on a magnetic field, you have to go around sort of a distance. You fuzzy out space by that amount, and any kind of periodicity can only happen on that scale. And so that roughly is the area occupied by a single quantum of flux. So hc over E, if you put in your units and do dimensional analysis, has the same units as magnetic flux. So this is a way of counting. And it also defines a length scale, and that length scale we'll come back to in a little bit. So what happens when we do this is that you get an interesting problem, because if you take a sample with magnetic field B and area A, well, you can compute the total flux, that's just multiplying these 2 numbers, and you can parcel it out into flux quanta. And it defines a number which tells you how many unit cells have I created in this little sample. And each of these levels has a degeneracy that corresponds to counting a whole sample and partitioning it into these many unit cells. And if you think about it, area is an extensive quantity in 2 dimensions, because if I double the sample, the area will double. That's what we mean. And so that means that there's this huge degeneracy, which, if you again go back to your second-year quantum mechanics, that means that you're going to have a very painful afternoon, because degenerate perturbation theory is horrible. So it turns out that there's a useful figure of merit. This is the number that Steve was using I don't know if he actually mentioned that he was using it, but you just count up. If I give you electrons are fermions, no anyons yet. And so if I put a fermion in one of these unit cells, it won't allow another fermion to come in. So I can count up the number of those flux quanta in my sample that have an electron or don't have an electron. And that tells me the fraction of the magnetic unit cells in the sample that are filled with electrons. So this means that there's a nice way of dividing our problem. When it's an integer, well, I just fill in, so let's imagine I have an imaginary system with 9 flux quanta and I give you 9 electrons. So this ratio is 9 over 9, which is 1. There's just a unique way to fill 9 electrons in 9 boxes because you can't put a second electron into any of these boxes. And so that's nice because I don't have to even worry about anything. I've got a unique ground state. So I've solved a many-body problem. There's no difficulty here. I don't have to care. The problem comes in when I go to fractional nu. So for instance, if I had 3 electrons in those 9 boxes, I've just written down 4 of the different ways you could arrange them. But in fact, I counted and there are 80 more that you can do. And the way you can see that is 9 choose 3, right? But of course, you have to be even more careful because electrons are fermions, so you actually have to worry about these things, think about the appropriate fermionic statistics, solve some big matrix. And in fact, a colleague of mine in grad school said, all this theoretical physics is just huffing and puffing, and then you diagonalize a big matrix. And the problem here is that the matrices are very big indeed. And so, in fact, what you do is you throw up your hands and guess. And that's really what Laughlin did to win the Nobel Prize, is in fact guess an answer more or less for this problem of 3 electrons in 9 boxes. So the magic is, of course, that we have physics that comes out of this, that if you you take a system which realizes this physics. Of course, the n is now in the scale of Avogadro's number. It's a gigantic scale, and you're putting lots of electrons in. And what you see is that what you measure is something pretty mundane. You measure longitudinal and transverse conductivities. And the big thing to take away from a plot, there are 2 things to take away from this plot, is that every time you see a plateau in the Hall conductivity, you've just seen a different phase of matter. So I can't even count the number of phases of matter on this plot. And the other remarkable thing is I'm tweaking between phases of matter. I'm toggling between them by just dialing a knob in my experiment that changes the electric field on a sample. So I'm changing a voltage, and I'm going between different phases of matter. So that's a pretty amazing plot if you think about the effort. Once you've made the sample, the effort required to go to different new physics is quite great. So what I want to do is unpack the ingredients that went into this plot, so the topology, correlations, and the tunability, and contrast what we would get if we wanted to realize this in a different platform than this very exotic setting of electrons in a high magnetic field. So that's the goal for what I want to do next. So the first ingredient is topology. And if you go back to your 3rd year condensed matter course, then Steve has a very nice textbook, and if you open that textbook, you see that electrons in solids satisfy the Schrodinger equation, but with a periodic potential. And Shivaji pointed this out in his talk, but I'll remind you that back in the 1930s, Felix Bloch pointed out that, the solutions to this problem are not plane waves, but they're almost plane waves. They look like they have a plane wave piece and a periodic function. And so the one trick, though, is that while plane waves can have any momenta, these states can only have certain momenta that live within this object called the Brillouin zone. And the thing to take away is that these energy levels now split up, so you get these things called energy bands. So they have a well-defined energy-momentum relation. It's no longer as simple as E of k equals p squared over 2m, E of p is p squared over 2m, except near extreme points of the band. But away from that, you see that there are gaps that separate these bands. And the other thing is that this object, this thing that replaces the momentum, is no longer a label that's allowed to freely wander to minus or plus infinity. It has to live in this one-dimensional example on a circle, and in higher dimensions on more complex, effectively on a torus. Right? And so these objects mean that your momentum has now become something different from what you expect in free space. And so this is the physics of energy bands. This looks very different from the physics of Landau levels. So how do we connect them? Well, that was mentioned by Shivaji. I won't go over the details of it, but it turns out that when you think about these energy bands, they can also have topology, and this is the thing called a Chern insulator, which it was understood. The first model of this was written down by Duncan Haldane, and the kind of understanding of this as a topological object was pioneered by David Thouless. And really, they won the Nobel Prize in 2016 for their work. And so the basic idea is that these, what you want to take away is these are ways of having your cake and eating it too, having the sort of topology of a Landau level, but still having these sort of block-like states of electrons that we associate with moving in periodic potentials. And so the the thing that characterizes by a single number, an integer called the Chern number. And if you fill up one of these bands, you get a response. So that would be an insulator. Filled bands give you insulators. And that response would be quantized in units of E squared over H. And in those units, the response is just given by the Chern number. So these realize the lattice version of what we were talking about. And just as an aside, where does the topology come from? That's another story. So if we think about the kind of picture that's sketched over here, what Haldane was pointing out is that you could have a very complicated magnetic field that averaged to 0 in a unit cell, but was non-zero in these regions A, B, and C. So you could have some very complicated magnetic fluxes. So an electron moving there would go through some very weird pattern in its Landau orbits within that unit cell. But in the end, when all the dust settles, what you find is that the electronic wave function in momentum space winds as it moves. And that's very similar. It turns out that winding in momentum space has a very similar effect to an Aharonov-Bohm phase in a magnetic field, that thing that I started with. And the result is that you get this kind of topology. And this kind of physics often arises in systems with strong spin-orbit coupling, you know, that chapter of atomic physics that you happily glossed over and forgot. So that was the first ingredient, so topology. We have a way of taking these topological ideas at the Landau level and sticking them into this much more kind of heavy-duty machinery of band theory, where you have electrons moving in periodic landscapes. The second ingredient is correlations, and maybe this is a little bit less familiar. Let me just say what I mean by correlations. So roughly speaking, all we're talking about when a condensed matter physicist like Steve, Shivaji, or myself are thinking about materials, typically what we're interested in is the competition between sort of two tendencies. And in some very coarse level, you can think of it as the age-old story of quantum mechanics. Is it a wave or is it a particle? Right? So you can sort of think about systems like insulators as in some sense being more localized. Electrons really look like individual charges sitting in potential wells and not hopping around. They don't know that they're moving. And so we would say that that tends to happen when things are much more strongly interacting, either with a lattice potential or with each other. In contrast, metals and superconductors have a behavior where they're much more wave-like. The electron actually explores all the sites. An individual electron is zipping around all over the sample. It doesn't stay tied to one site. And any material you give me will lie somewhere on a continuum of where it sits. It's never going to be ideally in one limit or the other. So that makes the quantum Hall effect a very special place, because in Landau levels, the kinetic energy is 0. So by definition, if I think of this as controlling interaction strength, well, one of the first things your tutor will tell you is dimensionless numbers, the only thing that mean anything. And so the dimensionless thing we should look at is the strength of interactions over this kinetic energy. But the kinetic energy in the quantum Hall effect is 0. There's no kinetic energy. All states are created equal. And so Landau levels intrinsically, if you sit in the middle of a Landau level, you're at infinitely strong interactions, which is why the problem was so hard to solve. So you're in this strong coupling limit. While that looks very difficult, it turns out that we have, after 30 years or so, good experience with what happens at strong coupling. Like we solve any problem, the extreme limits are always easy. Chern bands and topological bands in general, any bands are different because they have a kinetic energy. You've changed it a little bit, but the electrons still move. They're not sitting around stationary. And so they're an intermediate coupling, which is a fancy way of saying I don't know what to do. Right? They're just difficult because you don't have... Here you can think about, well, if I turn on interactions, I perturb around free particles. Here you say, oh, if I turn on interactions, I perturb around electrons sitting on sites. Here I don't know what the right basis is or what to do. So this is why these kinds of problems are difficult. And typically when you're here, theorists throw up their hands and argue for years. That's really what happens. And just to say that you can ask the same question, is it possible to get Chern insulators that look very much like the Landau level? Can we play games and take that kinetic energy and make it go away? So, about 15 years ago now, various groups came up with the idea, and it turns out that it was an idea that was sitting around just waiting for somebody to do it. It's not that difficult to think about. You can play with the way electrons move between sites in a unit cell so that you make the Chern band, so this is a topological band, but notice that while this band up here is doing a lot, if the electrons were here, it looks really like their kinetic energy is not doing anything. Whoops. And also looks like my laptop is not doing anything, so... Something about this room really doesn't like us getting to the right answer. So it turns out, under the right conditions, and it actually took some time, Shivaji and I thought a little bit about what those right conditions should be, along with a postdoc at Oxford, Rahul Roy, who actually did a lot of work on these topological ideas. It turns out, under the right conditions, you can more or less map the problems of a Chern band with a very weak dispersion to a Landau level. So it looks really like you can get pretty close to what the experiments what we would like to get, something which looks like it has the topology of a Chern band, lives in a crystal, so there's no need for a big magnetic field. The physics came from electrons moving in some kind of complicated crystal potential, and that has strong interactions. And there was lots of subsequent theory, but it turns out while theorists can write down flattening bands as just an equation, it's very, very hard to do an experiment. So that kind of made progress, held up progress for a very long time. And that brings me to the third ingredient. What would you like to be able to do? If, in order to do an experiment, you don't just want to create some particular material, you want to be able to tune things. You want to be able to dial a knob and access the physics that you like. And this is actually where another challenge comes in. So, ideally, we'd like to tune everything. If you ask a physicist, if an experimentalist comes to a theorist and asks, what would you like to tune? The theorist will say everything. But if you really had to pin me down and say, what is the one thing I would like to tune? It would be the density of electrons. And why that is if you think about the difference between the integer and the fractional quantum Hall effect, how I went from one to the other is by just changing the electron density. Here, I had a filled Landau level. I added a third of a Landau level's worth of electrons. That changed the electron density in the system. Similarly, if I took block bands, I have a band insulator when I fill bands, and if I add charge, then it'll go into the next set of bands, and then I could get a metal, or if there's strong interactions, I could get a kind of insulating state. And if these bands had topology, then you might get interesting topological states like Chern or fractional Chern insulators. So the key point is that density is what allows me to go from these integer states where correlations didn't matter to these fractional states where correlations mattered, where anyons live, and so on. So I really need to tune the density to get to these interesting states. So why is that difficult? So let's say I gave you a traditional material and said change the density. What you would actually do is go, and if it was a three-dimensional material, that would be grown in a lab by some very complicated, chemistry building next door. They would grow a sample. They would try and get the density by changing the kind of the exact alloying of two different elements in the sample. They would get some density. Then they would go and do it again and get the next point on the plot. So the time scale for that, and this is a very useful unit called GSY. Does anybody know what GSY stands for? It's a very, what? Exactly. So it's measured in graduate student years. So, it depends. If you have a lot of grant funding, that's a very short time scale indeed. But, times are tough, so we need to look for other answers. So two-dimensional systems offer a different idea. And this is essentially an instantaneous way to change the density. So I'm going to take you back to, something that probably could have even been given on your admissions interview. So I've given you a parallel plate capacitor, which has charge Q and minus Q on the two plates and a voltage. I'm going to give you some numbers. Not sure why it's doing that, but let's see. It's responding roughly like my tutorial students were when I give them this problem. So the typical numbers you could have here are a distance of about 10 nanometers. That's about the figure of merit of what we can do in most experiments. We can bring two atomically thin layers or two planes of a two-dimensional electron gas in these heterostructures to about 10 nanometers away from each other. The typical dielectric constant of these systems is about 10. And if I put much more than about a volt of potential difference between them, I start doing chemistry rather than physics, because I start changing the atoms, and we don't want to go there. So it's a simple exercise to see that the charge density, which is just the total charge over the area, the total charge is just the capacitance times the voltage over the area. There's a simple formula for a parallel plate capacitor that says that the capacitance is the area times the dielectric constant over the distance. So I get this nice formula for the charge density. And if I put in these numbers, I find that I can push about an electron in a square of size about 10 nanometers. So if I take this, so with these kind of experimental constraints, what I can do by changing the voltage by about 1 volt is change the density of electrons by putting about 1 electron every side of 10 nanometers square. So we want to ask, how does this compare to the length scales that we have at hand in a system? So the first case would be looking at the Landau level, and I said a length scale would make its appearance again. So the natural length scale in the quantum Hall effect, remember, if we think about the magnetic unit cell, that roughly has a scale LB, which is this quantity. I just put in the numbers for you. It's obviously magnetic field dependent, but it hits this nice scale of 10 nanometers at about 7 Tesla. And it goes up as the square root of B, so if I double this would go up to about, this would go down a little bit, so it would be about 7 nanometers or 8 nanometers, around 7 nanometers at 15 Tesla. And in fact, that plot I showed you, if you zoomed in, you would see it's about a 15 Tesla field. And if you look at this axis, I'm changing the voltage. Units are in actually volts. So in fact, I'm accessing many different quantum Hall states just by changing the voltage. And now you understand why I can do that, because I was changing the electronic density by about an electron every magnetic unit cell as I swept through these things. So that's the nice figure of merit. So now let's think about the scale if I actually handed you one of these Chern insulators in a crystal. So the typical lattice spacing in a crystal is a few angstroms. So let's just pick a convenient thing about 0.3 nanometers. And if you translate that into the density I can tune, I can get to about 1,000th of a unit cell. That's all I can do by any kind of experiment that involves gating the sample. It's very, very hard to push push more or less charge onto the system. So what I'm end up with is that even if we were to go to all the effort of realizing one of these amazing Chern insulators in a sample, you wouldn't actually be able to do anything with it without going back to this horrible way of looking at things in graduate student years, of trying to grow a new sample for every filling. That's the only way you could do it, even though you have this nice two-dimensional system. So just to summarize, this is the state of play that compares the two things. So we have Landau levels and we have Chern bands. Each of them has a notion of a filling, which basically counts, per level, what's the fraction of it is filled with electrons. So that's why we have this thing that distinguishes between integers and fractions. And so we got one thing right. We said, well, if we fill a Landau level, we get an integer quantum Hall insulator. You fill a Chern band, you get an integer Chern insulator. These are nice because these are not interacting. We understand a lot about these things. But now we see that we can readily tune the filling in one case, but we can't do it anything appreciable for a realistic crystal with a spacing of about 1/3 of a nanometer. And the other feature here is that we don't have, if you just gave me a Landau level, it comes for free with the fact that it has no dispersion. So it's intrinsically a very strongly interacting system. Whereas generically in a Chern band, I don't know that it's so strongly interacting that I would get these interesting states. Maybe I do all this work, put them in, the interactions aren't strong enough, and the system just remains a metal. That's a lot of work to get a metal, right? So that's the state of play. And so our challenge is clear. We want to get energy bands with these Chern numbers. We want correlations to be enhanced relative to the kinetic energy, and we want to be able to easily change the filling. Right? That's the three things we'd like to get. So hopefully it's clear why we need those ingredients. So let me give you the Hollywood version of that history. So what happened next? So, this is the situation in 2013. Theory is going far ahead of experiment. The reason you can tell this is an experimentalist is they're wearing a tie even when they're, relaxing at home. So, they're very distinguished. 2013 to 2018, because there were no experiments, theorists were doing a lot of very, very esoteric questions, ignoring experiment. In the meantime, experimentalists were working very, very hard. And so, to come to the natural end of that story, around 2018, there was new physics, right? And I want to tell you about that new physics in the time that's left. And I think I have about 20 minutes left, Andre. Is that roughly right? Great. Okay. So the new physics is something called the Moret effect. And so I went on to the internet and looked for a figure, and you get this rather nice piece of poetry which says, which is, making a riff on an old song by Dean Martin, right? So the Moret phenomenon is this rather remarkable thing, and it's sadly often capitalized because it sounds like it's the name of a person. The actual story is really interesting. It's a word that comes from the textile industry. So Moret fabrics actually has a long etymology all the way from Arabic to English and then via French back to English. And what it is basically is there are two things. If I were wearing stripes and you went back and watched this video, which I doubt you would do, you would see actually that because I'm being recorded on a screen with some refresh rate, often what you can see is that when people have two screens or when they have stripe patterns and they're being interrogated at a different frequency, you can see this weird pattern of beating interference. And so that's something that often comes in, and that's sort of a personal experience many of us have with Moret patterns. So what it is, it's really a very simple idea. If you have two periodic structures, and for whatever reason they have slightly, in one dimension, if they have slightly different frequencies, or in two dimensions, as you'll see in a minute, they have slightly different orientations, then you can actually get a certain type of interference pattern. So let's see how that works. So let's just take two waves. So I'm taking two waves which have so this delta is much smaller than k, what I'm going to think about. So I have two waves that very slightly differ in their, they're slightly offset with respect to each other, and you can see that, the red and the blue. And I add them up. And what you see coming out of this is this potential that looks awfully like a lot like it's periodic. It isn't really. It turns out that it's only periodic if somehow there's some kind of rational relationship between delta and k. You can think about this function and see if it's really periodic, and you can see that unless the peaks and troughs of what delta wants to do exactly line up with the peaks and troughs of k, this won't be really periodic. But gosh, it looks really very close to periodic, so it's faking me into thinking it's periodic. And so this is the Moiré effect. When you take two things which take two periodic functions and add them up, and they have a very slightly offset frequency, then you get an emergent approximate periodicity, which is much, much, much bigger than the microscopic periodicities of either of them. Right? So they both started out with a periodicity that's about 2 pi over k, but this sort of emergent long wavelength periodicity is something like 2 pi over delta, which is really big. So that's an emergent length scale. So this is all I can do in one dimension, but if you're in 2 dimensions, you can do something a little bit more exciting. So let me just pass that out so you can see for yourself how that works. So you can make 2-dimensional atomically thin materials, and you can actually play with those. So pass these up, send some to that side. And you can slap layers on, if you can just take one and pass them up. Yeah. You can take 2 atomically thin layers, place them on top of each other, and it turns out that the kind of atomically thin materials like graphene, one reason you can make them is because they crystallize to very strong bonds in 2 dimensions, but the interactions between the layers are held together, are only van der Waals interactions. They're very, very, very weak. So it turns out the way people first made graphene was remarkable. What they did was they took a piece of Scotch tape, stuck it on something that was effectively a very, very pure piece of pencil lead, and peeled it off, and just kept doing this. And if you do that enough times, you peel off an individual atomically thin layer, right? But you can do this twice, and by a lot of very hard work, and I don't want to, this is exactly what the hard graft of experimentalists. So my friend Andrea Young was one of the first people who did this. He was mentioned in Steve's talk, and he roughly says it's like you had a kilometer-long chopstick in each hand. You're taking a layer of cling film and trying to rotate it on another layer of cling film, all while not being able to see what you're doing, right? So that's roughly what people did. But they could do that. They could take 2 atomically thin layers, align them close to each other, and then just give them a little bit of a twist. And so when you do that, you get patterns like this, right? So the left is 2 kind of stripy patterns. The right is what happens when you take 2 hexagonal lattices and rotate them. And there's a little bit of algebra. You say, imagine each thing had a periodicity that was cosine k dot x in each direction. Well, the angle between the 2 vectors, they have the same length, but they're rotated relative to each other. And if you think about the difference between these 2 vectors, at small angles, it's just the size of the vector times theta, sort of a basic trigonometric calculation. And so if you think about the fact that the original periodicity was the lattice scale, which is the previously advertised 0.3 nanometer scale, that number was cleverly chosen because it is roughly the lattice spacing of graphene. And if I pick an angle of about 1.5 degrees, it turns out that this Moiré length scale is about that magic number of 10 nanometers. So what it means is if I made one of these samples and used it as one plate of my capacitor, that has a potential that's exactly matched to what I can push charge on and off at the 1 charge per unit cell level easily, right? So I can do that. So, of course, I'm not doing anything close to putting 1 charge per microscopic cell. What I'm doing is pushing off one electron in every one of these yellow squares. I can put one of these yellow little shaded regions, I can pop an electron on and off. So it's a very, very low density of electrons, and normally there wouldn't be a potential for it to push against. But by twisting this lattice, I've created a new potential. It's a much, much lower energy scale than the original potential. So while the original answer would be in around electron volt or 1/10 of an electron volt scale, we're down now to the milli-electron volt scale because a much, much lower energy scale. But if I do a very sensitive experiment, I can measure things at that scale. So that I'm now going to be playing with a periodic potential that sits at that scale. And another fact is that just as the magnetic field modifies the kinetic energy of free electrons, the fact that you have this potential turns out to give you flat bands with a very small kinetic energy. And the great thing about this is, and I'll come back to this in a little bit, there's a huge number of kinds of 2-dimensional materials. Graphene was the first discovered, but there are now there are libraries of them. I'll come back to that. So it means that there's essentially combinatorial possibilities for new physics. But the hydrogen atom of that new field is basically taking 2 graphene layers and twisting them. And so there's some extra details because graphene famously does not have electrons that look like free particles. They look more like Dirac particles. And that actually gives you some extra richness, which was noted by these 2 gentlemen, Rafi Bistritzer and Alan MacDonald. And they actually came up with a way, it turns out, to actually figure out what this lattice does, this new emergent superlattice does, is not easy. You have to figure out new ways to calculate with them, and they did that. And I hope what you can see here is by playing around with the angles, near that 1.25 degrees, what you see is a very, very flat band. there are sort of technical reasons why there are actually 8 bands in there, because electrons come with different spins and they have other kind of labels on them. But you get these 8 energy bands. And so from what I've told you so far, what you should be thinking about is that, well, I've got some boring insulator here, relatively boring, because after all, I just filled up these bands. It looks like the insulator in my textbook because I just have filled bands and then a gap to the next band. I should get a boring insulator here. And if you count, those boring insulators happen at fillings of -4 and 4. Why there are fillings of -4 and 4 is that graphene has some natural electron count. So -4 means I pull away 4 electrons in every one of those cells. +4 means I add 4 electrons to each of those cells. So I can look at things adding and subtracting charge to that system. But if I'm inside there, I have a interesting problem, because essentially the kinetic, so this, the width of this band, the thickness and energy, gives me a figure of merit for the kinetic energy. And actually the Coulomb interactions are much, much bigger than this. So it means that the electrons here are very, very strongly correlated, which means if I put charge on there, anything I see should be coming out as the result of the electrons talking to each other, rather than they're talking to the superlattice. And so the group of Pablo Herrero at MIT did this in about 2018. And in fact, what they found was that, yes, you see the boring, BI is for band insulator. It may as well be for boring insulator for this thing. So there's nothing interesting happening there. But what they saw was something very surprising. So you notice that there are 2, so what this curve is just showing you how conducting the sample is as I tune the gate voltage, as I push charge on and off the system. And what you see is, while it's really an insulator here and here, that I would have expected, that just came from this calculation of electrons talking to the weird Moiré lattice. But what happens here are 2 new insulators that nobody expected. Why is that insulating? It must be as a result of electron-electron interactions. So it turns out there were about 100 different proposals for what that insulator was, and sort of by luck or good judgment, Steve and I managed to propose the correct one, and that was confirmed in experiments a year or so ago. And there's another surprise, which is a surprise that still remains to be explained. So if you take those insulators and move a little bit away from them, you get a superconductor. Nobody expected that. Nobody expected graphene to become a superconductor in this situation. So you've taken an insulator, you've added a little bit of charge, and somehow magically the added charge becomes superconducting. We don't know why it becomes superconducting. There's a huge debate in the literature over this. We don't know what that superconductor is, whether it's like the old superconductors that people discovered in the that people explained successfully in the 1950s, or the newer high-temperature superconductors. We don't know what the mechanisms are. This is a big area of research that lots of people are trying to understand. And there's a whole bunch of other phenomena and some hints of topology. But it turned out that in graphene, it was very, very, very hard to get these topological states reliably. And in the end, the only way to get them reliably was to go back to the old idea of turning on a magnetic field and teasing them out. So that wasn't very satisfactory, because after all, the way we went into this was getting rid of the magnetic field entirely and trying to do this without a big magnetic field, without all these exotic effects. So we have a nice system, but only tantalizing hints of topology. And so can we do better? So indeed, the answer is that we can. And the reason that we can do better is because of the fact that there's this combinatorial richness to this new class of platforms. Old material science, you needed to know a lot of chemistry, because you needed to know, what things will combine with other things to form, good compounds. How would those compounds crystallize? Here, the nice idea here is that you have these 2D materials, and you can play combinatorics instead of chemistry. You can stack the materials on top of each other. You can twist them. You can pick different materials. You can try and use different place the resulting thing on a different substrate to change the nature of interactions between electrons. And so if you look at the library of 2D materials, there's actually a lot of them that can be Scotch taped. Of course, to get the best samples, you do something different than Scotch tape. You do chemical vapor deposition or something like that, but still the Scotch tape idea is pretty cool. And so there's a whole list of them, right? And so I'm not going to go into any of them except one. So there's a very important class of things called transition metal dichalcogenides, TMDs. There's molybdenum disulfide, which I think for many years was used as a lubricant or something like that. It turns out to be a very important compound for a lot of these experiments. And there's a whole family, and I'm going to focus on these. And so what these are, it doesn't look like this in this rendering, but they also have a honeycomb lattice. So it looks a little bit different than graphene, but if I looked at it on the 2D plane, it would have some honeycomb-like pattern. And it's made up of, unpacking the name, it's made up of transition metals like molybdenum, tungsten, or hafnium, and a chalcogen. A chalcogen is a fancy word for something in the same row as sulfur in the periodic table. So sulfur, selenium, or tellurium. So they're characterized by this rather neat fact that in any individual layer, they have something that looks like a parabolic dispersion. You don't have to worry too much. So it looks like we did all of this. It's not as rich as graphene in an individual layer, because graphene, after all, had this fancy Dirac electron floating around. None of that happens here. Instead, you have this it looks as though, apart from some label that the mass is a little bit different, it looks as though you could just start off with ordinary electrons in free space. But what's nice about it is that if you now take one layer of this TMD and place it in another layer, now electrons want to tunnel between the layers. And the potential that the two electrons, that electrons moving in this combined system see, are because of that tunneling. But that tunneling takes a particular form. So this delta captures the tunneling between the layers. And that essentially all that tunneling ends up doing is, there's also a different potential in the layer. So that delta, so sigma is some Pauli matrix. I won't write it down. That just, think of it as, just like I have spin, there's up spin and down spin, I can represent it as a spin. Imagine sigma plus is in the top layer, sigma pointing down is in the bottom layer. And sigma in the plane would be, you're in some superposition of the two layers with some definite phase. So it turns out that this, give me 1 second. What you find is that this delta is like it's a periodic field. It's got the periodicity of this emergent Moiré supercell. And that's like a Zeeman field that tells you which layer you want to be in. So the electron really wants to be in the layer it's told to be by that. And the kinetic energy goes along for the ride, because it doesn't care which layer you're in, roughly speaking. And it turns out that near some special angles, this delta forms a lattice, which is known as a skyrmion lattice. So Shivaji sketched what a skyrmion was. It's this configuration where you kind of wrap the sphere. So this is a kind of busy plot, but what this is saying is where this thing is yellow, roughly speaking, and the color is dark, your electron's entirely in the bottom layer. Where it's white, you're entirely in the top layer. And where it's in between, you have these blue arrows that tell you where on the equator you point. And if you look at this little diamond here, that's one unit cell. And if you count the topological index in that unit cell, following the rules that Shivaji gave you, there's one skyrmion in that unit cell. You go to the next unit cell, there's another skyrmion. Now, this skyrmion is in an abstract space. It isn't really spin. It's this layer skyrmion. But it turns out that this has really interesting consequences for the electrons. To see that, what you do is do something that we're all taught to do, is always go to a frame in which the problem looks simple. So we rotate so that we're always pointing in our layer coordinate is always pointing along the way we're told to point by delta. And if you do that change of basis, what you find is that the problem reduces to looking exactly like you get for electrons in a magnetic field. Like there's a vector potential that the electrons see, but there's also some effective potential landscape that they see. And each of these things is periodic with the periodicity of the unit cell. And it turns out that if this has one skyrmion per unit cell, that corresponds corresponds exactly to having one flux quantum per unit cell in this new problem. So what you've just done is realize effectively a Chern band, which is pretty flat. It turns out that's, if the dust settles, that's what you get. So let's go back to our wish list and see whether we get the thing. So it turns out there's a particular example that's very nice where the transition metal is molybdenum, the chalcogen is tellurium, so molybdenum ditelluride. And in typical physics fashion, when you twist them, you put a little t in front. So it's TMOT2 is the fancy word for this material. And it turns out if you take the angle of about 3.7 degrees, you get a Chern band that has a good gap to all the other bands. So you can get this topology. You've got the topology in there. The bands are flat with a kinetic energy that's much less than the interactions. So you've got correlations. And there's tunability. So the lattice spacing at this scale is about comparable, it gives you a Moiré length of about 10 nanometers, which is exactly what we can dial on and off with a 1 volt potential. And you can also, it turns out that the interlayer potential can be used to switch on and off the topology, which is kind of nice because sometimes it's nice, one of the best ways to show that you've got something is to show that you can controllably turn it off. And if you're an experimentalist, you really like the ability to switch things on and off. And in fact, when people made these samples, so this is actually the second experiment that were done on these. Now, they'll come back to the first experiments in a minute. So what you should see here is on the x-axis of these plots is that interlayered displacement field. When that's 0, the system forms this skyrmion lattice. And the blue curve is the Hall resistance, and the red curve is the longitudinal resistance. So you see the telltale signature of a quantum Hall-like response, a 0 longitudinal resistance, and a quantized Hall resistance at h over e squared. So you've just created an integer Chern insulator. But if you tweak that displacement field above a critical value, you turn off this skyrmion lattice, and bang, everything goes away. So you've actually controllably created a quantum Hall state. You couldn't do this in a Landau level because you don't have a knob to switch on and off the topology. Even more remarkably, if you now work a little bit harder, you can actually focus on a different density. So going from here to here is tuning the other knob, turning a dial on my gate so I can change the charge. And at this point, you're partially filling this band, and you find that there's a Hall resistance of 3h over 2e squared, or if you translate that into conductivity, that's like a two-thirds quantum Hall state. There's an active search for using these platforms to get a whole list of exotic states. So non-abelian anyons like Steve talked about, something more exotic states called fractional topological insulators. But again, one of the really remarkable things of why this field is exciting is that if you go back to the quantum Hall effect, so Steve talked about the work of Sui, Sormer, and Garsard, who are working in gallium arsenide samples. So for the fractional quantum Hall effect, other groups replicated it in gallium arsenide. But for it to be replicated in another material took about 10 years. So it's a very long time for it to be reproduced in a second material. So you might have been forgiven for thinking maybe there's some very special feature to this one material. Why should we care? Why is it a universal phenomenon? Whatever a theorist tells me. The time scale for the fractional Chern insulator to be reproduced was 10 weeks, because roughly. So just a few months after twisted MOT2, people did something in a completely different system, which is taking, when you do this exfoliation of graphene, you're trying to get a single layer, but sometimes you peel off 5 layers at a time. And somebody said, why don't we just stick that 5-layer sample and play with it and see what it does? And it turns out you can see a whole bunch of fractions for the same type of experiment. It turns out that this physics, it's about a year and a half old. There's still active debate over what's going on. Nobody understands this to any great detail. I'm very happy to say that one of my former students is one of the leading, I'm not involved in this work, so I can say it, is one of the leading people in trying to piece together what's happening in these materials. So it turns out there's some proposals that it realizes some new states of matter that are completely different in some ways from what we had expected from before. So just to comment a little bit on the future, so now that the tortoise of experiment has lapped us and they're going forward, theorists are having to come back and think a little bit more about how to model these states and also how to look for them. And so one of the things that Steve talked about is that a signature of the fractional quantum Hall effect is this idea of anyonic statistics. And the way you see it in a Landau level is by doing this edge state interferometry experiment that Shivaji proposed and Steve has talked about today. It turns out there's a wrinkle of that in these two-dimensional materials. The wrinkle is that, when you want to do transport measurements, you have to take gold or something like that, or platinum, and make electrodes and stick them on the sample. And chemistry doesn't like that. It turns out that only a couple of groups, I think at this stage, one group in the world knows how to make good contacts to these TMDs. So but the nice thing about a two-dimensional system is you can look at it, and you can look at it slightly more scientifically and put light in there. So it turns out the first way people looked at it is by some clever photoluminescence experiments that were allowed. There's a signature in this, which I won't go into, that explains that, if you see a kind of kink in this photoluminescence, you should imagine that there is a fractional state, there's an insulating state there. So this got us thinking, could we actually just use light to search for anyons? Can we just shine light on a sample and look for that? And, one of the things we're actively working on is, can you actually measure fractional statistics by shining light on samples? And at least in theory, the answer is yes. So we're working with experimental groups to realize those ideas. So just to illustrate that having a new platform not only allows us to realize old theoretical ideas, but forces us to think of new ways of doing things that we thought we knew how to do well before. So just in summary, since I'm out of time, by the simple idea of twisting two-dimensional materials, we're able to get a confluence of 3 key new routes to physics, routes to new physics. The idea that you want electronic states with some topology, where electrons strongly interact with each other, and where you have the tunability to actually see any of those phenomena. And I think this is the last time, and I'll just say, and I just gave a particular example of this richness of this setting to look for these integer and fractional Chern insulating states, but there's a whole bunch of other things you can look for, like the superconductors I talked about and so on. And so I think just to summarize, this idea of probing both familiar states but also seeking new ones using the versatility of these platforms is really increasingly a center of activity in the field of quantum condensed matter physics today. So let me close with that and take your questions. those are both extremely good questions. So let me answer the first. So non-abelian anyons, it's not the dimension of space. It's an interesting point. So Steve, I think, didn't quite mention non-abelian. So Steve talked about anyons. So anyons are generalizations of statistics where, instead of getting a -1 when you take a particle around, when you exchange two particles, you get a phase. So it turns out there are a class of systems where if you take a system of frozen anyons and you take one around, you swap them, instead of getting a phase, you get a matrix. And that turns out to be intimately linked to the fact that when you have, essentially when you have a bunch of anyons in your sample, if they're non-abelian, there are many possible degenerate ground states. And when you do this transformation, you're doing some kind of adiabatic rotation between the space of those states. And in fact, when Kitaev came up with this idea of quantum memory, really the non-abelian case is the one that's very rich for doing lots of quantum protected operations. So that's why the non-abelian one has this totemic significance. If you can achieve that, you can do a lot. So that's the first answer. The second answer is really very, very insightful because, in fact, if you take graphene and try and strain it, there are things that look a bit like gravitational fields and so on. It turns out for graphene, what really happens is that effectively you put on a magnetic vector potential on the sample. So it's sort of related but not quite the same thing. Now, for Moiré graphene, it turns out that, in fact, when you take two layers and stick them on top of each other, it may not surprise you that, while things are sort of happy being twisted, they're not thrilled with the idea, right? And so that puts lots of strains on the sample. So there's almost never a sample that lacks some kind of strain. And so most people just thought of this as an irrelevant complication, and they solved these problems which didn't have strain in them. They got all these disparate answers for why these insulators were forming in that graphene thing. I mean, led by our students and postdocs who insisted that this was important, Steve and I and our group took that quite seriously. And it turned out once you took that seriously, that explained why there were the insulators forming. And that's now the accepted explanation that it plays a very important role indeed. So it does play a role, and there are ways to engineer kind of gravitational-like phenomena, but not quite so straightforwardly as that. It's much easier to engineer electromagnetic phenomena with strain, if you like. I don't know if there's any sharp thing for neuroscience, because at some level, these are the kind of things that have most natural connections between sort of neuroscience ideas and condensed matter are things which have lots of randomness in them, lots of interconnections between particles. This looks much more like a plain vanilla crystal, just engineered in a clever way with some other wrinkles that make it different from the crystals we see all the time. So I'm not sure if there's a direct connection. My wife is a neuroscientist, so if there was one, I think it would create a lot more domestic harmony. But sadly, I'm not allowed to say I'm working on her stuff just yet. There is some work on trying to look at twisted nanotubes, but one of the things that comes about when you think about it is that really this two-dimensional twisting kind of requires you to be properly in two dimensions. So when you talk about nanotubes, it turns out you can sort of make an argument, but it has to be at some very, very rigid, specific angles. You can't sort of have this extra freedom. The other thing in nanotubes is you can get a moire by just looking at the kind of slight layer offset, or if you take two different nanotube materials, like something like that, like a copper nanotube and stuff. The extent to which that's been explored is not, of course, everything's been explored theoretically, right? People like to play these games. People have even talked about how to do it in 3 dimensions, because you can imagine that you do some optical lattice where you have, people can engineer motion of neutral atoms in electron clouds. When you cool atoms down, you can make optical potential, so they move trapped in atomic wells, and you can do whatever to some degree of whatever you like. You can do whatever you like in those samples, and you can actually mimic what happens when you twist 2 of them, or in photonic crystals. So people have done that. The problem with all those kinds of platforms is it's hard to engineer strong interactions in them. So while you can get there, for instance, photonic systems, actually getting strong interactions in a purely photonic system is very, very hard. So you can get some moire-like phenomena, but the full richness seems to be hard to achieve. It's possible, but it's not obvious how you would do it. Yeah, that's a great question. So I'm not an experimentalist, so what I'm going to tell you is my understanding of it. So there are various ways you could do it. I think the standard way is you kind of glue these, you kind of hold these samples onto, there are various ways to suspend these samples and stick onto them. There's ways to pick them up. So they exfoliate, grab, so there's this tear and stack. So you tear the material, you stack it, you lay it down, and you set it onto something. You take the other layer, and you're using all of these with nanomechanical manipulation, so you kind of know your angle, and you can twist it and drop it on there. Now, the success rate of this, Pablo's group is probably one of the best at doing it. I think they have something like a 60% success rate, something like that. But typical groups starting out start at something like 2 or 3%.
These are done at microkelvin temperature?
No, the actual preparation is not usually, the experiments are often at millikelvin, microkelvin temperatures. I don't know what the temperature scale of the preparation is. And now there are ways to make, one of the things is that originally we would actually exfoliate samples, but the best graphene is now chemical vapor deposited, and so it's better samples and so on. So the one thing that only one group in the world does is one of the materials I put there is hexagonal boron nitride, which is just like graphene, except the 2 carbon atoms in graphene are replaced by boron on one side and nitrogen on the other. That's a material that turns out to be hard to make in the sense that essentially there's one group in the world that makes it in Japan, and they supply the entire world essentially with this thing. So there are these 2 gentlemen, Takashi Taniguchi and Kenji Watanabe, who are on every single experimental paper on this material. If they don't give you HBN, you can't do an experiment, roughly speaking. And so that's the big material challenge, is getting good HBN. And the graphene stuff is assembly. Yeah. So I should say one last thing. There is a remarkable new experiment done in the group of Shahal Ilani, who's at the Weizmann Institute in Israel. What they've done is take an atomic force microscope, which you usually think of as a very, very sharp tip that you use to do atomic scale forces. And they did something very counterintuitive. They took that and just chopped its head off. So instead of having a sharp, pointy pyramid, they have a flat-topped pyramid with a kind of triangular profile. And they can drape a graphene layer on that pyramid, and it's about, what is it? I think it's about 200 nanometers by 200 nanometers in each side. So you've got this flat surface, and the graphene sticks pretty well, and it stays pretty flat. So they've got another graphene layer on top. They can bring that layer down and just twist. So they can actually twist in real time and watch all this physics come in by just twisting it. The experiments are just spectacular. And you can use this for all kinds of things. So this is the next frontier. And dozens of groups around the world are trying to make it now that Shahal has shown it can be done. Oh, that's fantastic. So actually for graphene, the magic angle is not completely crazy. There's a calculation you can do that rests on the fact that graphene has a linear dispersion. So what you can do is, maybe I'll just do that on the board. So you have this picture of, so this is the Brillouin zone of graphene. And the thing you need to know about the Brillouin zone of graphene is it has this thing called a Dirac cone at each of these corners. So let me focus at one corner. This has a linear dispersion. So if I look there, E would be like VF times K. Okay? So now imagine I have 2 such layers. So I have one Brillouin zone like this, and I have another one. I always mess this up, so let's see if I can do it. That's slightly offset. There we go. So I've twisted them relative to each other. So I have 2 such cones. Right? So you can see that in the same frame. So one's gone theta over 2 one side, one's gone minus theta over 2 the other side. So they started out on top of each other, they've moved. So in momentum space, if I drew a picture along the line that joins them, I would have a picture that looks something like this. Right? So this point goes here, this point goes there, and each of these has E going as VFK. Okay? So the 2 layers, the only perturbation I'm going to put in is when the 2 layers talk to each other. Do we have color? Yeah. Excellent. So let me actually make this work. So let's say let me just redraw these in color. So the orange one came here, the blue one came here. Each of these are contributed by the 2 layers. The only potential of the Moiré physics is when the 2 layers talk to each other. So if I think about a perturbation theory problem, there's not much to do here, there's not much to do here, but at this point I have a degeneracy and the 2 layers talk to each other. So the minute I switch on a potential, if you go back to your second year quantum mechanics, nature abhors a degeneracy, so you'll just make a gap over here, right? And so that is the potential, let's call that T-perp. That's the potential between the layers. So this gap is of order T-perp. So we want to ask how far this came out. Like what was this energy? This energy is, let's call this distance K. It turns out that distance K is like related to theta. It's just that it's a very small scale. It's related to theta. It's theta times some number that's known for graphene. Let me just write it that way. Okay? So I have 2 scales. I have VF times KD times theta. That's how high this energy is. So this is VF KD theta. And I have T-perp. This comes from chemistry. KD comes from chemistry. VF comes from chemistry. Theta is in my control. So if I set those 2 equal to each other, and choose theta that way. So if I just say, so all these numbers I know, what happens is that the band gets pushed down by as much as it went up. So it tries to rise and gets whacked down by exactly as much as it went up. So given that I know something from chemistry about how the 2 layers talk to each other, and these 2 are numbers from a single layer that I know from chemistry, I can actually predict an angle at where this happens, and this is remarkably good. That's actually an exact calculation of the magic angle. Now, the actual calculation of why that further terms don't push things apart again and so on requires some details. There's a fancier thing, but this gets you to within the level of accuracy I was talking about in the talk. This gives you the right number. Yeah. Thanks for asking.
Okay, I think we've run out, so thanks very much.
Thank you.